Welcome to Cloud Coffee and Certs, the podcast where we chat about cloud certifications, learning cloud skills, and staying confident on the tech journey. Grab your coffee, relax, and let's level up together.
Hey everyone, welcome to another episode of Cloud Coffee and Certs. Now, in this week's episode, we will be continuing our AWS Advanced Networking certification journey. We started with VPC Basics in the last week episode, and I will be continuing on that by putting some more building blocks onto the basic concepts. Also, I'll be covering one news which I am taking again from Hacker News, and I am dissecting that. I will be sharing my feedback onto that. I was only able to get one news, which to be honest is pretty old now. I was planning to record this episode last week, but because of the flu season here, I am the victim of one of that. So I was mostly into the bed, recovering myself, and of course, working on my day job. So I was not able to add anything onto that. I didn't get time to read more into like what sort of security news I can cover because of the missed episode. But that's fine. I mean, the news which I'm covering today is around cloud and cloud security, so it makes sense to continue and share that news with you guys. So after this break, we will be continuing to news first.
Let's hit pause on everything else for a moment and look at what's changing in the world of cloud and security lately.
Alright, welcome back. So today I want to talk to you about a recent report covered by Hacker News that highlights a surprising simple but serious cloud security issue. What it exposes is training applications, which can be used as an entry point for crypto mining attacks inside the enterprise environment. Now, it sounds like pretty simple attack. I mean, it doesn't sound like really sophisticated nation state kind of attack or a brand new 0-day vulnerability kind of thing. In fact, and that's why it's so important, because the issue wasn't a cutting edge exploitation. It's just a basic exposure misconfiguration, or just a simple fix which normally in organizations we don't apply. So according to a research from Pantera Labs, many organizations, including the large enterprises, intentionally keep vulnerable training or demo applications exposed to public internet, which is often used for security awareness training and penetration test, or maybe internal demonstration, POCs, etc. And they are deliberately kept as insecure by design. And that's the whole point. The problem is not the existence of these application itself. The problem is they are deliberately left publicly accessible. And in some cases, they are actually connected to real cloud environment in the background with some meaningful permissions, or maybe someone who can traverse from entering into this application to the main enterprise environment. Now, if you think about that for a second, an application is designed to be vulnerable and is deployed in a live cloud account. It's reachable from internet. It may have access to some roles or identities that can interact with other resources in that environment. In fact, I have seen in my own experience, sometimes people tend to reuse the configuration name. So maybe they have created a role which is having access to this like demo environment, and they might be creating a role with minor tweaking which have access to a different environment as well. Or maybe sometimes people reuse the same role because they don't want to create a new set of credential or new set of IAM roles to for different use cases. They can reuse the same infra as a code. So it all connects back to a good coding habit as well. If you are writing everything, if you are creating everything from using infra as a code, don't try to just copy paste and run the same code in a different account. It will create an identical configuration into a different account. Anyone who have access to that account then can of course guess what the credential are in other account as well. Now, back to this news, it turns a training tool actually into an attack vector now. So what researchers reportedly found that a significant portion of these exposed training environment, they show a real sign of compromise. Attackers were deploying crypto mining softwares, web shells. There are some logging around persistent mechanisms as well. So this means that they aren't just theoretical attacks, they were actively exploited in the real environment. And crypto mining in enterprise cloud environments is particularly attractive to attackers because it generates revenue for them. If someone can compromise a cloud workload and quietly run their mining software, for example, they are effectively turning your compute bill into their income stream. So it's your compute, it's your resource, You are paying that to maybe your cloud provider, maybe to AWS or Azure, but who is generating revenue from that? Person who is running their own workload inside that compute environment. So that what makes this situation more concerning, because it reflects a broader pattern in cloud security. Attackers are increasingly exploiting misconfigurations rather than waiting for a complex software flows, and that's one of the thing, right? I mean, if you see even in the real environment, when we see that not everyone is planning for a complex heist and trying to steal the stuff from maybe some sort of like a museum, or maybe having a bank robbery, advanced bank robbery. People just do petty crimes as well, right? So that's exactly same in the cybersecurity world as well. Not everyone can do complex software attacks or flaws, but they can exploit just a simple misconfiguration as well. And everyone is trying to scan for exposed services, overly permission identities, forgotten environments, or maybe weak lifecycle management. So if you created a demo environment, maybe which was used in one of your POCs or one of your customers' use case, but you forgot to discontinue or decommission that, then of course that lingering compute is always there for people to just access anytime. In many cases, they don't need any advanced techniques as well to access these applications. All they need is visibility in your exposed attack surface. Now, that's the thing with training environments. They often fall into gray area because they are not production and they may not be monitored as closely as well. And I've seen in my own experience, if you have like a training environment, and if you try to implement more security tools around that, or maybe a secure infrastructure, a perimeter security around them, people tend to oppose that. People, I mean, who are accessing those training environment, they tend to oppose that because of course from their perspective it's just a demo environment. They don't want the day-to-day security blocking them from doing simple testing, because that's the whole point of having that training environment. So they might not even be going through a same security review process while installing new applications, or new maybe custom softwares, or maybe something from or some open source tooling to test few stuff. And they are often, because they are often assumed as temporary, right? So no one cares about them. But in cloud environments, temporary resources have a habit of becoming a permanent resource. So maybe someone spins up an environment for a workshop or demo, it works, and soon people will be like, yeah, that's nice, can we keep it as it is, like running as it is? And soon that will become like a norm. That application is always there, it's still there, publicly accessible, not monitored as well, and even connected to real infrastructure. Maybe the use case is that you have created that demo application, but you need some data from production to test or to show the results in front of the customer. If you keep that connection to the real infrastructure to get the data in, then of course the connection is there, right? So that's exactly the blind spot attackers will look for. Now, another important takeaway is privilege management, because even if trailing application is exposed, its impact should be limited. But if it has like access to overly permissive IAM roles, or if it's running in a VPC with broad connectivity to other resource, compromise of one that single instance can become like a lateral traverse movement into wider environment. So this is where principles like least privileged network segmentation, which we will be covering in our AWS Advanced Network Security as well, and strict identity boundaries become very critical. A vulnerable app used for training should never have like same permissions with the production overload, and that's a simple concept, but not everyone follow that in demo environment. Monitoring is another key missing stuff, because if your organization prioritizes on logging and detection in production environment, but they are applying like lighter controls on development training accounts, then attackers don't care about your internal labels. If they read something like in demo environment, they'll find it valuable. They can easily exploit that, and there's no alert for what happened into that demo environment. The broader lesson here is simple but powerful. Every deployed asset, every application, every compute resource onto your environment can be acted or can be used as an attack surface. So it doesn't matter whether it's production, staging, development, or training. If it's exposed and connected, it must be secure and monitored accordingly. So this incident reinforces an uncomfortable truth about cloud security, which is most breaches don't begin with like some sort of advanced hacking. They can begin with simple but basic forgotten service, or a deployed environment which is not used anymore, but have some sort of like overprivileged identity attached, or it's connected to real infrastructure or your enterprise backend. And when organization they scale quickly into the cloud, these basics they are harder to follow. So if you don't have like strong governance, you don't have good asset inventory, life cycle control, as well as monitoring of like who can access what, then it will become very hard when you put more and more infra onto the cloud. So what's the result of this? Like what we come out of the as a conclusion of it, this isn't a story about like sophisticated attackers breaking through hardened defenses. I mean, if you came to this episode thinking like maybe I'll be covering some advanced vulnerability today, unfortunately not covering something that. It's just a simple story of like having some sort of like operational discipline. It's about visibility. It's about understanding that temporary and low risk are not security control. If you are running a cloud environment, especially at enterprise scale, you need to define clear ownership of all assets. You need to have some sort of automated discovery of all the exposed services. You need to strictly control the IAM boundaries. And of course, you have to consistently monitor across every account and your environment into maybe in AWS or any other cloud provider, to be honest, because attackers don't care about whether it's training or production, whether they are finding something useful into that compute itself. But if they can traverse from, or they can move from this training to your real production environment easily, then you're as easily exposed as anything else. So what attackers really care about is what's secure and what's exposed. And if your exposed application is a demo application, they won't care about it. All they want is they are looking for some open door, and if you are giving them that open door, then of course anyone can come in. So that's the whole point of having the advanced network security as well, because when you are putting network segmentation, when you are putting like defense in depth, and one of depth or one of the layer in that security is networking, if you are making sure that all the different type of workloads are completely secluded, if you have like a known production or demo environment, that should never ever touch to the production in any case. So if you ensure all those aspects, then of course you are more secure compared to like if you are just peering every VPC with another VPC, or because of some use case you did it temporarily but you just left it as it is. So yeah, I really wanted to cover this news because it's very basic. It's having simple concepts. It's covering a simple attack vector, but it's really important and it's somehow linked to what we are covering in this podcast as well, or in this examination as well. So after this announcement break, let's move into our main episode and cover the next building blocks of AWS VPCs.
Let's level up, refill coffees, and dive into the main episode.
All right, so today we are talking about two services that are sort of at the heart or core of AWS networking architecture. One of them is Route 53 and Transit Gateway. Another one is load balancers. We have already covered VPC basics in terms of what is a VPC, what we have in terms of like public and private subnetting, and how we can use internet gateway and net gateways to ensure that our application can connect to internet but securely. Now, in this week's episode, we will be understanding about DNS, transit gateway, which deals with VPC peering or connecting one VPC with another VPC, and of course, load balancer, which normally sit in front of your application, kind of acting as a ingress or egress to the traffic to your workloads. Let's start with Route 53 first. If you have built like anything beyond a simple single VPC setup, which we normally do if we are setting up our demo account or if we are building a new AWS infrastructure for the first time, almost certainly touched one of these. I mean, Route 53 and Transit Gateway, they usually come. You may have used these services, but in enterprise cloud environment, they are kind of like must to have and they are used everywhere. So starting with Route 53, it's a AWS managed DNS service. At basic level, it's just another DNS which help in acting as kind of like a phone book. So when someone types in a domain name and it just translates that name into an IP address, so traffic knows where to go. So that translation is what DNS does. 53 handles that translation, but it does much more than simply mapping names to IP addresses. It's not just a simple DNS. When you create domain like maybe in case of mine, it's technocoffee.com, Route 53 can direct that traffic to application load balancer as well. It can direct that traffic to EC2 instance or maybe S3 static website or even something outside of the AWS. So it's not just a simple routing. It can really make intelligent decisions as well. For example, if I deploy my application in London and I'm deploying another application like a standby or maybe active active application in Frankfurt or Virginia. With latency-based routing, Route 53 can automatically send users to the region with the lowest latency. A user in the UK will always hit the London application, while a user in Germany will be hitting that local Frankfurt application. So we don't need like a custom logic inside our application. DNS handles it for us and requests reach to the correct infrastructure. Route 53 also can perform health checks if your primary endpoint goes down. So if your one of the application goes down, Route 53 can automatically fail over to the secondary endpoint, which essentially means that redirection happens at the DNS layer itself. So you don't have to put another layer for the redirection use case only. Let's shift gears and maybe we talk about transit gateways now. Transit gateway solves a different problem. While Route 53 we just now discussed, it deals with name resolutions. Transit gateway deals with network routing. To be clear, it is deciding where the actual packet movement will happen between the networks. So before, transit gateways didn't exist, or if in today's scenario, if you don't want to use transit gateways, VPCs together to connect together, they need VPC peering, which works fine in small scale. I mean, you can connect one VPC to another VPC using VPC peering. But as the number of VPCs grows, and if you have maybe multi-region deployments as well, this becomes really complex because pairing then becomes very messy and it's very hard to control like which VPCs peer to what. Five VPCs will create maybe a 10 peering connection because if you do perform like one to one mapping between those five VPCs, they will need a 10 connection. And if you have like another five VPCs, then it adds like another one. So it gets scales really badly. And in terms of like at the enterprise level, that becomes very painful to manage, and of course it's nearly impossible as well. Who will maintain it? So transit gateway introduces a new kind of like a hub spoke model which we used to have in our classic networking infrastructure as well. Instead of every VPC connecting to every other VPC, all we have to do is we have to ensure VPCs connect to a central transit gateway, and that gateway becomes the routing hub. So it simplifies the architecture, of course, it centralizes the control, and of course it's easy to scale as well because now we have hub spoke model instead of a full mesh kind of deployment. Now, if we imagine it in terms of maybe a company which is having separate VPCs for production, development, and security, plus maybe a connectivity back to on-premises data center, Transit Gateway can connect all of those. It can also do site-to-site VPNs as well. You can create direct connect links. You can, of course, use Transit Gateways for connectivity across multiple accounts. So it essentially becomes kind of your cloud router for whole organization. And if you think a design which use both Route 53 and transit gateways, we can maybe think of Route 53 telling us where something lives, like where a particular application is hosted, which IP address, and transit gateway will ensure that there is a path to go there. So think of maybe Route 53 as your maybe GPS, which tells you the destination, and transit gateway maybe can be a road or motorway network that allows you to go from one city to another city. So that's the whole sort of analogy if you compare it from how Route 53 and Transit Gateway can be used. So in a real world enterprise design, we might deploy one transit gateway per region. Then we can attach all the environment VPCs to those transit gateways, and we can attach our VPN or direct connection connect back to on-prem, and we can of course configure Route 53 private hosted zones for internal name resolution. With that setup, internal services resolve cleanly, traffic flows through control paths, and of course, scaling from one VPC to 5 or 10 VPCs is easily manageable. Now, here I just now mentioned about a private hosted zone. So that's another key thing. Route 53 provide both private and public hosted zones. Public hosted zones are those domains which you want to resolve from internet. So for example, if you have a public facing website or application, you have to host that DNS entry into a public hosted zone. Only then it can be accessible on the internet. But if you, for example, have an internal application which only need to be resolved from internal network, you don't want people outside your organization to access that application, then you can create a private hosted zone, and you can use that private hosted zone as a DNS to domain to internally resolve your application within private network. So that's the concept of private and public hosted zones as well. If you think from the perspective both Route 53 and transit gateways, they are really important services, and they can work together as well. You can even use either of them if you don't have a use case of like multi VPC peering. Then of course transit gateway is not a mandatory service, but of course you need to know those services, because if you want to put an infrastructure and you want to make sure that it's scalable as well, you need to make sure you are using the correct service. Now, moving on from transit gateway and route 53 to load balancers, let's see what they are and why they are used in AWS as well. Now, if we create an application, we of course have to scale it beyond a single server to make sure it's highly available. Moment we start discussing about like enterprise scale and making an application HA or geo red, we are already stepping into a load balancing scenario, because at its core, a load balancing does exactly what the name is saying. It distributes incoming traffic across multiple targets, and those targets can be EC2, containers, IP addresses, or maybe even serverless functions as well. Instead of users connecting directly to one backend server, now they are connecting to load balancer. So a load balancer decides where that request should go. And why is it important though? Why we are distributing it? Because a single server is a single point of failure. If it crashes, your application goes down. Even if it's not crashing, if it just gets overloaded, then performance will suffer. People might be complaining about latency, your application is not responding properly, and load balancer just solves all these problems, because if it improves availability, and of course it ensure that we can easily create some sort of backend which is scaling as well. In AWS, load balancing is provided through different services. An umbrella service for that is Elastic Load Balancing. Inside that, we have multiple different type of load balancers depending on which layer of your OSI model your load balancer is working. So, for example, the most commonly used one is application layer load balancer, which easily maps with the layer 7 of OSI, which is application layer. And if you remember what layer 7 is, it deals with HTTP and HTTPS. So you can inspect the request and make the routing decision based on things like your web headers, URL paths, query strings, or HTTP headers as well. So imagine if you are running a web application where request should be going to some domain slash API to one service, and another should be slash images or slash backend to another, we can use application load balancer to make that decision for us. So it will route based on what's mentioned in the HTTP header, and it will perform the routing and it will send the traffic to the correct backend. This is a scenario for path-based routing. We can also create host-based routing as well. So traffic for maybe technocoffee.com goes to one backend, and admin.technocoffee.com goes to another. Admin.technocoffee.com doesn't exist if you want to try, but yeah, I can create like multiple domain level decisions as well. And even though they are sharing the same load balancer, the traffic based on different web address, they will go to different destinations. So this makes application load balancer ideal for architectures where we are using containers or modern web applications. So it's more cloud native. It tightly integrates with services like EKS or Kubernetes. It supports WebSockets, HTTP 2, making it well suited for real time applications. Now, next we have network load balancer, which operates as layer 4 or transport layer. So it doesn't care about the HTTP traffic, it cares about TCP and UDP connection. So it routes the traffic based on IP addresses and port. And because it's operating on lower level or lower layer, it's extremely fast, capable of handling like millions of requests per second with low latency. So it's designed for performance and scales. And I think questions might come around in which scenario, in the scenario where you want like better performance, what you should be using. So of course, NLB is the answer. So we typically use network load balancer when we need ultra high performance static IP addresses, or when we are dealing with non-HTTP protocol. For example, if we are running a service which is using a custom TCP port, we can easily use network load balancer. We shouldn't be using application load balancer in that case. Then there is gateway load balancer as well, which is a bit different than network and application. It is designed to deploy third party virtual application. So if you are using firewalls, if you are using a third party firewall onto the cloud, then you can use gateway load balancer to distribute the traffic onto different firewall applications which you have created, maybe IDS or deep packet inspection tools. So instead of distributing traffic to application server, it is distributing traffic to the security applications which you have created. So it's commonly used in centralized inspection architecture, or maybe where we want all the traffic to pass to a single security layer before reaching its destination. So it's widely used there. And of course, the concept is pretty powerful when we think from the enterprise perspective, because we want our enterprise to secure on the parameter itself. So we can maybe create a hub spoke model using transit gateways, and we can use gateway load balancer to make sure that your firewall appliances integrated with the transit gateway is acting as a single point from where you are ingress or egressing your traffic. And finally, there is classic load balancer as well, which was actually the original older offering, and I don't think they sell it anymore. It's considered kind of legacy, and AWS recommends that we should either use application or network load balancers. So I don't think there's any point of talking about classic load balancers anymore. Now let's talk about simple, maybe different use cases practically where these load balancer can be used. I already highlighted few of them, but one of them like application level load balancing, where we are requiring maybe intelligent routing, SSL termination, or we want to have integration with web application firewalls. We can use application load balancers. If we are building something which is performance sensitive, like maybe high throughput system or maybe real time streaming backend, network load balancer are better suited for that use case. And one of the key thing is network load balancer also provides static IP support. So if you have use case where you want to make sure that the IP address which is associated with the load balancer always remains same, then we have to use network load balancer, because they does provide that static IP support service. And if you are using a simple security focus architecture, then of course gateway load balancer is the only one which is designed specifically for that. And load balancer does play a highly critical role in the availability as well. So for example, if I place target across multiple availability zone, I can resist on them behind a load balancer, and load balancer will automatically distribute traffic across the zones. So if one of the availability zone itself is experiencing some issue, we can shift the traffic to a better healthy targets in the other zones. So health check is one of the central key process around this load balancing. Each load balancer continuously checks the health of its register targets. If one of the target fails, then of course traffic will be stopped being sent to that target. And if the target recovers, traffic will automatically resume on that backend. Load balancers also support SSL termination, which means you can manage your certificates on the load balancer itself. So we don't have to manage or set up the certificates on the backend servers. We can install the certificates on the load balancer, and which of course makes it easier and more cloud native as well, because then you can use AWS Certificate Manager, which is AWS provided certification service to integrate with your load balancer, and the traffic and the certificate will be automatically applied on the load balancer. So the encryption and decryption using TLS will be simplified and will be having better efficiency as well, because now the termination is happening on the load balancer, not on your backend. So that's why load balancer, I think they provide a lot of interesting and advanced use cases, and of course they provide abstraction as well. So the client or the users who are accessing your services, they only know the load balancer IP addresses or load balancer detail. They don't know what's happening behind the scenes, or which or how many servers are responsible behind the scenes. So that's why I think understanding the different type of load balancer and the use case is one of the building block for designing the architecture on AWS as well, and of course AWS Advanced Network Certification exam as well. So I wanted to cover all these basic building blocks today, and I think we are more or less covered from the basics of the modern cloud VPC architecture. From next week episode, we will be starting our domain one. So we will be now discussing and covering our actual certification topics, because now we are well aware of what basic services looks like in terms of networking perspective. I'm not covering CloudWatch and CloudTrail or other associated services, which will be covered as part of one a few of the use case or domain topics, but I'm not covering basics of them because they are kind of like AWS service basics as a whole. So if you are already a cloud practitioner on AWS, then you might already be aware of those services. I don't want to go detail into them, because that's honestly, if we start covering each service which is even remotely associated with networking, but if we start covering those basic services as well, then it's never ending, because AWS have a lot of services which can be used in one way or another. So I'm just wanting to cover the basic building blocks from the AWS networking perspective, and from next week episode we will be covering our domain topics. Goodbye and good luck.
Been listening to Cloud, Coffee and Certs. Thanks for tuning in. Don't forget to follow and share if you enjoyed this episode. Until next time, keep learning and keep growing.